Dear students, today we are going to discuss two important conclusions of spatial theory of relativity, and those conclusions are length contraction and time dilation. These two things are basically the conclusions of or the consequences of the second postulate of spatial theory of relativity. And what is the second postulate is that the velocity of light in vacuum remains constant independent of the inertial frame, the source or the observer, right? Now let us go back to what we have done in the previous video. We have talked about Lorentz transformation equations that serve as a standard convention in describing the events pertaining to spatial theory of relativity. And what are the four equations, the master equations? Those are x dash is equal to x minus vt divided by 1 minus v square by c square. Similarly, y dash is equal to y, z dash is equal to z, and t dash is equal to t minus vx by c square whole divided by 1 minus v square by c square. Now, using these set of equations and using the previous knowledge that we did in the previous video, today we will describe two important consequences of spatial theory of relativity, that is length contraction and time dilation. That means that moving lengths appear shorter. Those lengths which are moving, or those objects or systems which are moving with velocities approximating the velocity of light, to an observer they will appear shorter. But of course, the condition is that the object must have to move with the velocity nearing the velocity of light. Otherwise, that's not true, because in the day-to-day life, we don't observe any kinds of events, any kinds of such events. The reason is that our ordinary velocities, no matter how high, they do not approximate in any case the velocity of light. And the second consequence is time dilation. By time dilation, we mean that the clocks tick slower, so that the count is less to keep the L by T ratio constant. Yes, we have discussed that in the previous video. Now let us take up these things one by one. First, length contraction. So again, let us choose two inertial frames, S and S prime. Observers are O and O prime. And remember, this S prime is moving with a constant velocity v with respect to this S. But before making you understand the phenomena of this length contraction and time dilation, you need to understand the concepts of rest and motion in true terms. What do they mean? See, when we talk about rest and motion, they have to be talked about together with observer and observed. Suppose this is the observer. This is the observer. It is moving. If there is an object which is also moving with this velocity v, there is no relative motion between these two. So this is a rest frame of reference. This will be called as a rest frame of reference. Now, this reference frame is moving, but the object that it observes is at rest. So there is a relative motion between the two. So we will call it a moving frame of reference. Similarly, in this frame of reference, we have an object that is at rest and this frame is at rest. So this is a rest frame of reference. Totally, it is a rest frame of reference. But then we have an object which is moving with certain velocity, but this frame is at rest. So there is a relative motion between the two. So we say it is a moving frame of reference. So when both are at rest, both the observer and the observed are at rest, it is truly a rest frame of reference. And when both the observer and the observed are in motion with the same velocity, again it is a rest frame of reference. By rest frame, we mean that whatever lengths and times you measure over there, they will be called absolute length and absolute time. But in case the observer is moving and the observed is at rest, or vice versa, that is, there is a relative motion between the two, then whatever lengths and times you observe, they are not absolute but they are relative. That's all. Now we will proceed to this concept of length contraction. If you have understood that, then we'll proceed to this. So let us choose a rod and I place it directly on the x-axis of this reference frame, moving reference frame, right? What do? I intend to measure the length of the rod from the perspective of observer O prime and observer O. Now, from the perspective of this observer O prime, Obviously, the coordinates of the rod are x1 prime and x2 prime. And because I have placed the rod on the x-axis, so the rod is also moving with the reference frame. So there is no relative motion between the object and the frame of reference. So whatever lengths you measure over here will be called as the absolute length. So L naught will be x2 prime minus x1 prime. Now what about the perception of this observer O? For this rod is moving with certain velocity v with respect to this observer O. So it will try to measure these two endpoints of the rod at the same time. See, here I want to take a pause and make you understand one important thing. Suppose I am standing at a rest frame of reference and I intend to find the length of a rod or a table or a chair. What do? Is that I find the coordinates of one end and then another end, and then I subtract the two. That gives me the length. But in case this rod, this table or this chair is moving with respect to me with certain velocity, then I have to take care that I have to do the two measurements of two ends at the same time. Here I cannot afford to take any time, any relaxation in between measuring the two ends of the rod. This is because the time that I take to relax, the time that I take to rest, in that time, since this object is moving, it will travel certain distance and the coordinates will change. I will not get the good parameters. Therefore, in case an object is moving with respect to the observer has to take care that he needs to take the two measurements simultaneously at same time. But for an observer who is observing the object in a rest frame of reference, he can take the liberty of taking certain time between one end and another end, right? Now, for this observer, obviously, he has to take the measurements at the same time, but here there is a relaxation, right? So, from the perspective of observer L, this O, length will be x2 minus x1. And then we can relate this x1 prime, x2 and x2 prime by using the Lorentz transformation equations, and let us see what do we get. We get that this x2 prime will be x2 minus vt divided by 1 minus v square by c square, and similarly x1 prime will be x1 minus vt whole divided by 1 minus v square by c square. Now this length is obviously x2 bar minus x1 bar or x1 prime. Now once I subtract these two factors, what do I get? x2 minus x1 in the numerator. In the denominator we have a common factor, 1 minus v square by c square. And why did I choose the same time? Again by the same description that I told you earlier. Because this observer, for whom the coordinates of the rod are x1 and x2, his time is but same. He has done this measurement at the same time. Therefore, I did not write T2 here or T1 here, because T2 and T1 are same. This observer has done the measurement of the rod, the two ends of the rod at the same time. He cannot afford to take two times, to choose two times. He cannot afford to do it, because in that case he is going to get wrong readings. He has, because the object is moving with respect to this, he has to take the two measurements at the same time. Therefore, this T1 and T2 are the same, and that is why I have written T in both the expressions. Now, all I mean to say is that once I subtract this factor from this factor, this Vt and Vt will get cancelled, and we are essentially left with, so we are left with x2 prime minus x1 prime is equal to x2 minus x1 divided by 1 minus v square by c square. So what is this? This is L naught. You know that, absolute length, the length which has been measured while being at rest with respect to the rod, right? And this is the relative length, that is L. So divided by this factor, 1 minus v square by c square. Therefore, what essentially do you get at the end? You get this L is equal to L naught times 1 minus v square by c square. Because we know that this factor is going to be less than 1. So this will diminish it. This will diminish this L naught. Therefore, L is less than L naught. That's what we mean. That moving lengths are shorter than the absolute lengths from the perspective of spatial theory of relativity. And not just in terms of perspective, but in terms of observation as well, direct experimental confirmations as well, right? So that is length contraction. The second thing is time dilation. So we'll move to that. So again we choose two reference frames, S and S prime, right? This is at rest and this is possessing a uniform velocity v with respect to this S frame. Now suppose I choose a coordinate x and I fix it. And then I observe an event at certain time t1. And then at the same position I observe another event at certain time t2. So what is the time interval between the two events? Obviously that is t naught, absolute time. And that will be given by t2 minus t1. And why do I call it absolute? Because I am observing this thing from a rest frame of reference. And I have fixed a position. I have not changed it. I am looking at the two events that happened at two different times, but from the same position and from a rest frame of reference. That is why the time interval that I measured between these two events that I call as the absolute time difference, right? So I denote that by t naught. So t naught is t2 minus t1. But what about the perspective of this S prime? For S prime, this t will be t2 dash minus t1 dash. And then we already have Lorentz transformation equations to connect these two coordinates. So what does that write? So t prime is t minus vx by c square divided by 1 minus v square by c square. Now once I do that, what do I get? I get t2 minus t1 for this. Once I choose the inverse equations, I get t2 dash minus t1 dash. Yes? So I think I need to rewrite it. So call this time as absolute time. And this is relative. Right? So this is relative. Now we need to connect these two equations in terms of this equation, right? So for T2 you are going to write T2 dash is equal to T2 minus this, and for T1 dash you are going to write, so let me write it on the side, that T2 dash is equal to T2 minus Vx by c square divided by 1 minus V square by c square. Similarly for T1 dash you can write this is T1 minus Vx by c square whole divided by 1 minus v square and c square. And again by the same argument as earlier, that I did not choose to write x2 and x1 because this observer has taken these two measurements at the same position. So we don't need to write x2 and x1 because x2 and x1 are essentially the same and they are equal to x, right? So once we substitute that here, this and this factor will cancel out and we are left with t2 minus t1 only. So T1 dash or T2 dash minus T1 dash will be equal to T2 minus T1 whole divided by 1 minus V square by C square. The other two factors are cancelled out, right? So what do we get? That this T is equal to T naught by 1 minus V square by C square. Again, because this factor is less than 1, this is going to increase the value of this T naught, right? So this T will be greater than T naught. So if you want to sum up the conclusions of spatial theory of relativity, all you can say is that a moving length appears shorter, and when the time is observed from such kind of a reference frame, it appears to be dilated, it is longer, right? So those are the, I hope that it gives you a basic, fair, preliminary idea, introductory idea about the spatial theory of relativity, its postulates, its conclusions. But of course, the chapter is not closed. It further lands you into curiosity. Keep reading and keep asking your questions. And do not forget to make comments in the comment section. That's it.